Hello, in this lecture we'll talk about the limit of a sequence. A sequence is a set of numbers, and a sequence can be finite, like the sequence 1, 3, 1, 5, 7 that consists only with 3 terms. So this is a finite sequence, and it also could be an infinite sequence, that is to say, the sequence of the natural numbers, the set of the natural numbers consists of infinite terms. So the set of the natural numbers and consists of the numbers 1, 2, 3, 4, 5, 6, 7 until n. So this is the set of the natural numbers. It is a sequence that consists infinite terms. Okay, so in this lecture we talk only about sequences that consist of infinite terms, like the natural numbers. So the limit of a sequence is the value that the terms of the sequence tends to, and is often denoted using the lim symbol. So here you can write down that the limit of sequence an when n tends to infinity equals to L, and L is any real number again. The limit of sequence an when n tends to infinity equals to L. Any sequence that has a limit, it is defined as a convergent. So this sequence an, is convergent because it has a limit. And any sequence like sequence Bn, if sequence Bn doesn't have any limit, then it is defined as divergent sequence. Okay? Actually, the limit of a sequence is said to be the fundamental notion on which the whole of mathematical analysis ultimately rests. So actually, a number L that belongs to the natural numbers is the limit of sequence an when n tends to infinity. Again, sequence an when n tends to infinity, the limit of this sequence is equals to L, and L is any real number. That is to say, L belongs to R, that is the real numbers, the limit of sequence an when n tends to infinity is equals to L if the numbers in the sequence an become closer and closer to L and not to any other number. I'll repeat again. L is the limit of sequence an when n tends to infinity only and only if the terms of sequence an are becoming closer and closer to L when n tends to infinity. Okay? So, what is the definition of the limit of sequence an? We call L the limit of sequence an when n tends to infinity. We can also write down that an, the limit of sequence an, is equal to L. So there are two ways to write down that the limit of sequence an is equals to L when n tends to infinity. Either we can write down that limit an when n tends to infinity is equals to L, and the second way to write down that the limit of sequence an is equals to L when n tends to infinity is an with the arrow to the right side that is equal to L. So only if the following condition holds, we can say that the limit of sequence an is equals to L. Only so the following condition must hold in order that the limit of sequence an will be equal to L. The condition is that for each real number epsilon that is greater than 0, there exists a natural number capital N such that for every natural number n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. So only and only if this condition holds, we can say that the limit of sequence an when n tends to infinity is equals to L. I'll repeat again. For every positive epsilon as small as we would like, must exist capital N that belongs to the natural numbers, and for every n that is also belongs to the natural numbers, for every n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. Or in other words, this condition states that the terms of sequence an are close to the limit L up to epsilon. Okay? So actually, if the limit of sequence an is equals to L, L is the limit of sequence an, then the environment of L will start from L minus epsilon and ends at point L plus epsilon, and the radius of the environment L is equals to epsilon. Okay. So in order that sequence AN, the limit of sequence AN will be equal to L when n tends to infinity, most of the terms of sequence AN must be located inside those two brackets from L minus epsilon until L plus epsilon. Actually, until n, we have fixed the terms that are not in the vicinity of L, and inside the vicinity of L, or inside those two brackets, that is the vicinity of L, we have infinite terms of sequence AL that are inside the vicinity of L. That is to say, we have infinite terms of the sequence AL that are inside those two brackets. So only if we have infinite terms of sequence AN that are inside those two brackets, that is to say, they are inside, they are in the vicinity of L, only and only then we can say that the limit of sequence AN when n tends to infinity is equals to L. So actually, symbolically, we can write down that for every epsilon that is greater than 0, there exists capital N that belongs to the natural numbers. So for every n that belongs to the natural numbers, or for every n that is greater than capital N, we will get that the absolute value of AN minus the limit L is less than epsilon. Okay, I repeat that only if this condition holds, then we can say that the limit of sequence AN is equals to L when n tends to infinity. I repeat on the condition that must hold for every epsilon as small as we would like, and epsilon also must be a positive number. There exists capital N that belongs to the natural numbers, and for every n that is also belongs to the natural numbers, for every n that is greater than capital N, we will get that the absolute value of AN minus L is less than epsilon. That is to say, from the index n onwards, all the terms of sequence AN, they are actually close to the limit L up to epsilon. Okay? I'll repeat again. This condition means that the terms of sequence AN from n onwards, from the index n onwards, are close to the limit L up to epsilon. Why? Because the absolute value of AN minus the limit L is less than epsilon. It means that from the index n onwards, if you subtract the limit L from any term of the sequence from n onwards, we will get that the absolute value of the term an minus the limit L will be less than epsilon. It means that the terms of sequence an from the index n onwards are close to the limit epsilon, are close to the limit L up to epsilon. Okay? Again, the terms of the sequence from the index n onwards are close to the limit L up to epsilon. That is the meaning of this condition. So this condition must hold in order that the limit of sequence an will be equal to L. And L is any real number. L belongs to R, to the real numbers. Okay? So I'll repeat again that we can say that the limit an, the sequence an converges. Okay? Sequence an converges to the limit L. So if this condition holds, then sequence an converges to the limit L. Only if this condition holds. Okay? So until now we talked about limits, finite limits. Here L is a finite number, it belongs to the real numbers. So we talked about sequences that has a finite limit. In the next step we will talk about sequences that converge in the broader sense. That is to say, we will talk about sequences that converges to either plus infinity or to minus infinity. So they are convergent in the broader sense. So the next topic is about infinite limits. Okay? That is to say, we will talk about sequences that has a limit in the broadest sense. That is to say, we will talk about sequences that has a limit of either plus infinity or minus infinity. So actually those sequences, we can say about those sequences that has a limit of plus infinity or minus infinity, that they are convergent in the broadest sense. Okay? So again we have sequence an. So the limit of sequence an when n tends to infinity is equals to plus infinite so I'll give you a definition when the limit of a sequence will be equal to plus infinite, which condition must hold in order that the limit of sequence an will be equal to plus infinity when n tends to infinity. So only if the following condition holds, the limit of sequence an when n tends to infinity will be equal to plus infinite. Actually, for every real number k, as large as we would like, there is a natural number n, such that for every natural number n that is greater than capital N, we will get that an is greater than k. So only and only if this condition holds, we can say that the limit of sequence an when n tends to infinity is equals to infinite, to plus infinite. Okay? So here k, the number k belongs to the real numbers, and k is as large as we want. So you will give me number k as large as you want, and I must find out capital N that belongs to the natural numbers, and for every n that is also belongs to the capital numbers, for every n that is also belongs to the natural numbers, for every n that is greater than capital N, the terms of the sequence must be greater than k. Okay? Again, for every k as large as you want that you give me, I must give you capital N, and for every n that is greater than capital N, that is to say all the numbers from the index n onwards, all the numbers, all the terms of the sequence an from n onwards are greater than the number k that you gave me. Only if this condition holds, we can say that the limit of sequence an when n tends to infinity is equals to plus infinite. Okay? So actually, symbolically, we can write down that for every k that belongs to the natural numbers, for every k as large as you want that you will give me, I must give you capital N that belongs to the natural numbers, and for n that is greater than capital N, and n is also belongs to the capital number, to the natural numbers. So for every n that is greater than capital N, we will get that an is greater than k. That is to say, from the index n onwards, all the numbers of the sequence an are greater than k. And because of the fact that k is a very large number, we can say that the sequence terms from n onwards eventually are larger than any fixed k, and therefore the limit of sequence an when n tends to infinity is equals to plus infinite. Okay? So only if this condition holds, we can say that the limit of sequence an when n tends to infinity is plus infinite. Again, for any k as large as you want that belongs to the real numbers that you will give me, I must give you capital N that belongs to the natural numbers, and for every n that is greater than capital N, and n also belongs to the natural numbers, for every n that is greater than capital N, we will get that an is greater than k. In other words, we can say that from the index n onwards, all the terms of sequence an are greater than k. And because of the fact that k is a very large number, as large as you want, we actually proved that the terms of sequence an are larger than any large number, and therefore we have actually infinite terms of sequence an that are larger than any number, and therefore the limit of sequence an when n tends to infinity is equals to plus infinite. So that is the condition that must hold in order that the limit of sequence an when n tends to plus infinity will be equal to plus infinite. So here we have the limit of sequence an that equals to plus infinite. Okay, and only if this condition holds, we can say that the limit of sequence an when n tends to infinity is equal to plus infinite. So in the next step, I will give you an example for a sequence that the limit of it is equals to plus infinite. So actually, the set of the natural numbers, that is to say, the sequence an is equals to n. That is how we write down all the natural numbers. Here, when n equals to 1, an equals to n. So the first number is 1. When n equals to 2, a2 equals to 2. That is to say, the second theorem of the set of the natural numbers is 2. When n equals to 3, a3 equals to 3. Okay? And the other theorem of sequence an will be equal to 100, etc., etc. And when an so it will goes until n. Okay, that is the definition of the natural numbers, the set of the natural numbers, and we will prove that the limit of the sequence of the natural numbers when n tends to infinity is equals to plus infinite. Okay? As you can see here, whenever n increases, the terms of the sequence are also increases. If n equals to million, then the theorem n for the index n that is equals to million, the theorem is also a million is equals to million, to 1 million. So when n increases, the theorems of sequence an, that is the set of the natural numbers, are also increases. And actually there is no limit to the set of the natural numbers, and therefore we can say that the limit of the natural numbers in the broadest sense will be equal to plus infinite. Okay, now we will prove according to the condition that must hold, that the condition, in order that the set of the natural numbers, the limit of the set of the natural numbers will be equal to plus infinity holds, and therefore the limit of the set of the natural numbers is equal to plus infinity. Why? Because the condition holds. So what is the condition? The condition is that for every k as large as you want that you will give me, I must give you capital N that belongs to the natural numbers, and for every n that is greater than capital N, and n also belongs to the natural numbers, we will get that the theorem of the sequence, that is to say an, will be greater than k. Okay? So here we will choose n, so you give me the number k that is as large as you want, and I will give you the index capital N that is a natural number, and I can choose the n that I will give you. So I will choose n that is equal to the integer of k plus 1 when it is rounded up. For example, if we have the number 5.5, when it is rounded up, it will be equal to 6. Okay? So in this way, we actually changed the theorem k plus 1 to a natural number. Why? Because it is rounded up, and therefore it will become a natural number. Okay, so I will choose n that is equals to k plus 1 for the integer of k plus 1 when it is rounded up. And so for every n that is greater than n, for every n that is greater than capital N, that is to say from the index n onwards, we will get that an is greater than k. So why an is greater than k? Because according to the definition of the natural numbers, an is equals to n an is equals to n, and we took n that is greater than capital N, and we know that capital N, we choose capital N, that is the integer of k plus 1 when it is rounded up. This is the integer of k plus 1 when it is rounded up. So here we have the inequality that n is greater than the integer of k plus 1 when it is rounded up. So if n is greater than k plus 1 when it is rounded up, let alone that n will be greater than k. Again, if n is greater than k plus 1, let alone that n will be greater than k. Okay, so we actually proved that for n, when you give me k that is a large number as large as you wish, I will choose n, natural number n, that is equals to the integer of k plus 1 when it is rounded up. And from the beginning, we choose n that is greater than n. Then from the beginning, we choose n that is greater than capital N. And according of what we choose capital N that is equals to the integer of k plus 1 when it is rounded up. Okay? And we choose also n that is greater than capital N. So this is true according to what we choose. This equality is true according to what we choose. That is to say, we know according to what we choose that n is greater than the integer of k plus 1 when it is rounded up, and if n is greater than the integer of k plus 1 when it is rounded up, let alone that s is greater than k, because k plus 1 when it is rounded up, it is greater than k. So if n is greater than k plus 1, let alone that n is greater than k. So you gave me the k as large as you wish, and I give you the capital N that is equals to the integer of k plus 1 when it is rounded up, and at the end we proved that n is greater than k, and that is exactly what we have to prove in order that the limit of the natural numbers will be equal to plus infinity when n tends to infinity. So we actually proved that the limit of the natural numbers when n tends to infinity is equals to plus infinity. Why? Because this is the condition that must hold in order that the limit of the natural numbers will be equal to plus infinity. Okay? For every k that you will give me, I must give you capital N, and I choose capital N that is equals to the integer of k plus 1, and it is rounded up. And for every n that is greater than capital N, and here capital N equals to the integer of k plus 1 when it is rounded up. So if n is greater than the integer of k plus 1 when it is rounded up, let alone that n is greater than k, because k plus 1 is greater than k. And if n is greater than k plus 1, let alone that n is greater than k. So the condition holds, and therefore the limit of the set of the natural numbers when n tends to infinity is equals to plus infinity. So we proved that the limit of the natural numbers is equals to plus infinity. Okay, so in the next step I will present to you what is the definition, in which condition the definition, the limit of a sequence will be equal to minus infinity. Okay? So similarly, we say that a sequence an, when n tends to infinity, will be equal to minus infinity. Or we can write down also that an, when n tends to infinity, is equals to minus infinity only if the following condition holds. So those are two ways to write down that the limit of sequence an when n tends to infinity equals to minus infinity. So either we will write down that the limit of sequence an when n tends to infinity is equals to minus infinity, or a second way to write down that the limit of sequence an when n tends to infinity is equals to minus infinity is to write down an with the right arrow that is equals to the limit of minus infinity. So only if the following condition holds, we can say that the limit of sequence an when n tends to infinity is equals to minus infinity. The condition is that for every real number k, there is a natural number n, such that for every natural number n that is greater than capital N, we will get that the term of the sequence an is smaller than k. So only and only if this condition holds, we can say that the limit of sequence an when n tends to infinity will be equal to minus infinity. Okay? So for any k as small as we want, we will have to find out capital N that belongs to the natural numbers, and for every natural number n that is greater than capital N, we will get that the terms of the sequence are less than k. That is to say, from the index n onwards, all the terms of sequence an are less than k, are smaller than k. In this way, we actually proved that the terms of sequence an from the index n onwards are smaller than any small number that you can imagine, and therefore the limit of sequence an when n tends to infinity in the broadest sense will be equal to minus infinity. Okay, so symbolically, or that is to say, the sequence terms are eventually smaller than any fixed k, and therefore the limit of sequence an will be equal to minus infinity. So symbolically, we can write down the condition that must hold in this way, that for every k that belongs to the real numbers, as small as you wish, we can find out capital N that belongs to the natural numbers, and for every n that is also belongs to the natural numbers, n belongs to the natural numbers, and for every n that is greater than capital N, we will get that an is smaller than k. That is to say, from the index n onwards, all the terms of sequence an are smaller than k. That is to say, in this way we actually proved that the terms, that infinite terms of sequence an are smaller than k, and k is as small as you wish, and therefore the terms of sequence an, the limit of terms, or the limit of sequence an will be equal to minus infinity if this condition holds. Okay? So, in the next step, I will present to you the arithmetic of limits. Okay? We have 6 rules that are connected to the arithmetic of limits. So actually, if the limit of sequence an when n tends to infinity exists, and also the limit of sequence bn when n tends to infinity also exists. So if those two limits of sequence an and bn exists, then we have 5 equations that are true, or 6 equations that are true. The first equation that is true is that the limit of sequence an plus bn is equal to the limit of sequence an when n tends to infinity plus the limit of sequence bn when n tends to infinity. And the second equation that is also true is that the limit of sequence an minus sequence bn when n tends to infinity is equals to the limit of sequence an when n tends to infinity plus the limit of sequence bn when n equals to infinity. That is the second equation that is true. We also have the third equation. According to the third equation, here we have C that belongs to the real numbers. That is to say, it belongs to R, the real numbers. So the limit of the sequence C times an is equals to C times the limit of sequence an when n tends to infinity. In other words, we can take out C out of the limit. In other words, the limit of C times n will be equal to C times the limit of the sequence an when n tends to infinity. We have also equation number 4. According to equation number 4, the limit of sequence an times sequence bn when n tends to infinity is equals to the limit of sequence an times the limit of sequence bn when n tends to infinity. Repeat again, the limit of sequence an times bn when n tends to infinity will be equal to the limit of sequence an when n equals to infinity times the limit of sequence bn when n tends to infinity. And we have also equation number 5 that is true. According to equation number 5, the limit of sequence an over bn when n tends to infinity is equals to the limit of an when n tends to infinity over the limit of sequence Bn when n tends to infinity. And finally, we have a question number 6 that is also true. According to question number 6, the limit of the sequence an to the power of p when n tends to infinity is equal to the limit of sequence an when n tends to infinity to the power of p. Okay? I'll repeat again, the limit of sequence an to the power of p when n tends to infinity equals to the limit of sequence an when n tends to infinity to the power of p. Okay? So, in the next step, I'll summarize the lecture. So, in this lecture, we talk about the limit of a sequence. I remind you that a sequence is a set of numbers. We have a finite sequence like this sequence that consists of only 3 terms, and we also have infinite sequence like the set of the natural numbers. It is a sequence that consists of infinite terms, and therefore it is infinite sequence, or it is a sequence that consists of infinite terms. And the way that we write down that the limit of sequence an when n tends to infinity is equals to n, that is the first way to write it down. And we also write down that an with the right arrow equals to L. That is the second way to write down that the limit of sequence an when n tends to infinity is equals to L. So any sequence that has a limit, so here L belongs to the natural number, to the natural numbers, L belongs to the real numbers, that is to say it belongs to R. R is the abbreviation for the real numbers. So when a sequence n, when a sequence an has a limit that is equal to L, that is to say it has a finite limit, then we can say that sequence A, n, is convergent. And if sequence Bn doesn't have a limit, then we can say that sequence Bn is divergent sequence. Okay. So, as I've already mentioned 2 minutes ago, we have two different ways to write down that the limit of sequence an when n tends to infinity is equals to L. Either we will write down that lim of sequence an when n tends to infinity is equals to L, and L belongs to the real numbers. And the second way to write down that the limit of sequence an when n tends to infinity is equals to n is an with the right arrow that is equal to L. So, in order that a sequence will have a limit that is L belongs to the real numbers. So, in order that a sequence will have a finite limit, the following condition must hold. The condition is that for every epsilon that is a positive number, as small as we wish, we must find out capital N that belongs to the natural numbers, and for every n that is greater than capital N, and n also belongs to the natural numbers, for every n that is greater than capital N, we will get that the absolute value of an minus L is smaller than epsilon. So actually, the meaning of this condition is that the terms of the sequence an from the index n onwards are close to the limit L up to epsilon. That is the meaning of this condition. And this condition must hold in order that sequence an will have the limit L when n tends to infinity. Okay, the condition is that for every epsilon that is a positive number and it is as small as we wish, we have to find out capital N that belongs to the natural numbers, and for every n that is also belongs to the natural numbers, for every n that is greater than capital N, we will get that the absolute value of an minus L is less than epsilon. And the meaning of this condition is that the terms of sequence an from the index n onwards are close to the limit L up to epsilon. That is to say, if the limit of this sequence an is L, then here L is at this point. So most of the terms of the sequence of an must be located inside those two brackets. The bracket starts from L minus epsilon and it ends here at L plus epsilon. And epsilon is the radius of the limit L. Okay, so this is the vicinity of L, or the environment of L. Okay, so when a sequence an has the limit L, then most of its members must be located inside the environment of L, and the environment of L is between those two brackets. So infinite members of sequence AN must be located inside those two brackets. And because of the fact that until the index n we have fixed terms, and from n onwards, that is to say from n until plus infinity, we have infinite terms of sequence AN. That is to say infinite terms of sequence AN must be located between those two brackets. In order that sequence AN will have the limit L, infinite terms of sequence AN must be located in the environment of L. That is to say infinite terms of sequence AN must be located between those two brackets. So symbolically we can write down that sequence AN and n tends to infinity will be equal to L only if for every epsilon that is a positive number, then it is also as small as we wish, we can find out capital N that belongs to the natural numbers, and for every n that is also belongs to the natural numbers, for every n that is greater than capital N, we will get that the absolute value of AN minus L is less than epsilon. Okay? So if sequence AN has a limit L, then we can say about sequence AN that it converges to the limit L. I repeat again that the meaning of this sequence and the meaning of this condition is that the terms of the sequence from index n onwards are close to the limit L up to epsilon. Okay? Here you can see that inside those two brackets each point is close to L up to epsilon. Each point is close to the limit L up to epsilon. So that is the meaning of this condition. So this condition must hold in order that sequence AN will have the limit L when n tends to infinity. Okay? So, as I already mentioned before, L belongs to the real numbers, therefore L is a finite limit. So until now we talked about a finite limit, but a sequence can have also a limit that is infinite. Okay? So here sequence AN when n tends to infinity can have also a limit in the broadest sense. That is to say, sequence AN when n tends to infinity can have either a limit of plus infinite, or it is also can have also a limit that is equal to minus infinity, but not both simultaneously. Any sequence that has a limit, it will have only one and not any other limit. So sequence AN, if sequence AN has a limit in the broadest sense, then it will have either the limit of plus infinity or the limit of minus infinity. So what is the condition of a sequence an, which condition must hold in order that the sequence an will have the limit of plus infinity when n tends to infinite. The condition that must hold is as follows. For every k as large as we want, we have to find out a capital N that belongs to the natural numbers, and for every n that is greater than capital N, and n also belongs to the natural numbers, for every n that is greater than capital N, we'll get that an is greater than k. That is to say, in this way we actually proved that the terms of sequence an from n onwards are greater than any big number k, and therefore actually infinite terms of sequence an are greater than k, and therefore the limit of sequence an when n tends to infinity is equals to plus infinity. So that is the condition that must hold in order that sequence an will have the limit of plus infinity. So symbolically, the condition will be written as follows. For every k as large as you wish, and k belongs to the real numbers, for every k as large as you wish, we have to find out capital N that belongs to the natural numbers, and for every n that is greater than capital N, we will get that an is greater than k. That is to say, from the index n onwards, all the terms of the sequence an are greater than k. Actually, we have infinite terms of sequence an that are greater than k, and therefore the limit of sequence an is equals to plus infinity. Okay? Then we proved that the limit of the set of the natural numbers is plus infinity. Here, the way to write down the terms of the set of the natural numbers is an equals to n. That is to say, when n equals to 1, the first term will be equal also to 1. When the index n equals to 2, then a2 equals to 2. a3 equals to 3. a100 equals to 100. And an equals to n. So as you can see here, whenever n increases, the terms of the sequence are also increases, and therefore we can guess that the terms of the sequence are greater than any real number. That is to say, the terms of the sequence are getting closer and closer to plus infinity, or the limit of the terms of the set of the natural numbers will be equal to plus infinity when n tends to infinity. And so in the next step we'll prove that the condition holds, that the condition for a sequence that has a limit of plus infinity holds, and therefore the limit of the set of the natural numbers is equals to plus infinity. Okay, so for every k as large as you wish, we have to find out capital N that belongs to the natural numbers, and for every n that is greater than capital N, and n also it belongs to the natural numbers, we will get that an is greater than k. So in this way we actually will prove that the terms of the sequence are greater than any great number k, and therefore the limit of the sequence of the natural numbers will be equal to plus infinity. So for any k that you will give me, as large as you want, I will have to find out capital N, and for every n that is greater than capital N, that is to say from the index n onwards, all the terms of the sequence of the natural numbers must be greater than k. So in order that this condition will hold, we will choose capital N that is equals to the integer of k plus 1 when it is rounded up, so we'll take the integer value of k plus 1 rounded up. For example, the number 5.5 when it is rounded up is equal to 6. So we'll take the integer of k plus 1 when it is rounded up, and so it will be equal to capital N. So for every n that is greater than n, then for every n that is greater than capital N, we will get that an is greater than k. And why an is greater than k? Because of the fact that from the beginning we will choose n that is greater than capital N. And according to our selection, we choose capital N that is equal to the integer of k plus 1 when it is rounded up. So here capital N equals to the integer of k plus 1 when it is rounded up according to our selection. And n is greater than capital N also according to our selection. Okay? So, and the terms of the natural numbers are defined as an equals to n. So from this inequality we can write down that n is greater than the integer of k plus 1 when it is rounded up. So if n is greater than the integer of k plus 1 when it is rounded up, let alone that n is greater than k. Why? Because k plus 1 when it is rounded up is greater than k. So if n is greater than k plus 1, let alone that n is greater than k. Actually, we proved the condition that must hold in order that the limit of sequence an will be equal to plus infinity. Therefore, we proved that the limit of sequence an, that is actually the set of the natural numbers, when n tends to infinity, is equal to plus infinity. Why? We actually proved that the condition that must hold in order that the limit of sequence an will be equal to plus infinity holds, and therefore we proved that the limit of the natural numbers is equal to plus infinity. Okay? In the next step, I presented to you Actually, what is the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to minus infinity? We can also write down that an with the right arrow equals to minus infinity. So what is the condition that must hold in order that the sequence an, that the limit of sequence an when n tends to infinity will be equal to minus infinity? The condition that must hold is that for every k as small as you wish, we have to find out capital N that belongs to the natural numbers, and for n that is also belongs to the natural numbers, for n that is greater than capital N, we will get that an will be smaller than k. That is to say, from the index n onwards, all the terms of sequence an will be smaller than k. And therefore we actually proved that the terms of sequence an are smaller than any small number k, and therefore the terms of sequence an when n tends to infinity will be equal, the limit of this sequence will be equal to minus infinity. Why? Because it is the terms of the sequence an when n tends to infinity are smaller than any real number that you wish, and therefore the limit of this sequence an will be equal to minus infinity. So symbolically we will write the condition that must hold as follows. For every k as small as you wish, and k belongs to the real numbers, we will find out n that belongs to the natural numbers, and for n that is also belongs to the natural numbers, for n that is greater than n, we will get that an is smaller than k. That is to say, from the index n onwards, all the terms of sequence an are smaller than k. And because of the fact that the terms, that infinite terms of sequence an are smaller than the number k that is as small as you wish, we actually proved that the limit of sequence an when n tends to infinity is equals to minus infinity. So that is the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to minus infinity. Okay? Then I presented to you the arithmetic of the limits. Here, if the limit of sequence an when n tends to infinity exists, and also if the limit of sequence bn when n tends to infinity also exists, so if those two limits exist, then equation number 1 is true, and according to equation number 1, lim an plus bn will be equal to lim an when n tends to infinity plus lim bn when n tends to infinity. Okay? And we also have the second equation that is true. Lim an, here actually we have n tends to infinity, n tends to infinity. So lim an plus bn when n tends to infinity will be equal to lim an when n tends to infinity plus lim bn when n tends to infinity. Then we also have equation number 2 that is true. Equation number 2 that is true. According to equation number 2, lim an minus bn when n tends to infinity will be equal to lim an when n tends to infinity plus lim bn when n tends to infinity. And we also have equation number 3 That is true. Here C belongs to the natural numbers. C belongs to the real numbers. C is any real number that you wish. So lim, when here n tends to infinity also, of course, lim C times an when n tends to infinity will be equal to C times lim an when n tends to infinity. And as I already mentioned before, C belongs to the real numbers. It is any real number. Okay? And we have equation number 4 that is also true. According to equation number 4, lim an times bn when n tends to infinity equals to lim an when n tends to infinity times lim bn when n tends to infinity. And we also have equation number 5 that is true. According to equation number 5, we get that lim an over bn when n tends to infinity equals to lim an when n tends to infinity over lim bn when n tends to infinity. And here I must add that lim bn when n tends to infinity must not equal to 0, because if lim bn when n tends to infinity equals to 0, here we divide by 0, and it is not allowable to divide by 0. Therefore lim bn when n tends to infinity must not equal to 0. Okay, and finally we have equation number 6 that states that lim an to the power of p when n tends to infinity equals to lim an when n tends to infinity to the power of p. That is to say, we actually can calculate the limit of an when n tends to infinity, and only after we found out the limit of an when n tends to infinity, we will raise it to the power of p, and it will be equal to lim an to the power of p when n tends to infinity. So the meaning of this equation is that we first of all can find out the limit of an when n tends to infinity, and only then we will raise it to the power of p, and it will be equal exactly to the same limit of an to the power of p when n tends to infinity. Okay, so that's it. Thank you very much.